Gentlemen, welcome to another one of my webinars through Ascendo Reliability. For those of you who don't know me, my name's Chris Jackson. If you want to find out more about me, obviously the Ascendo Reliability website has my details. But today's discussion is going to be about process capability analysis. And before we go into what that is and what that means, I'll just remind people that for my webinars, you get access to a guidebook, which is a downloadable, editable PDF document, which contains all the information, and in today's case, a little bit more than what we go through in the webinar itself. So you don't need to take copious notes, and all the information should be contained in there. Now, process capability analysis. What is that? Some of you might have heard of it. Some of you might not have heard of it. Some of you might have been forced here at gunpoint to learn about what PCA is all about. And I will stress that today's webinar really needs to follow on from the last webinar I delivered on statistical process control. And so we do need to be aware of what one is when we're talking about the other. So before we go into the details of what process capability analysis is and how it relates to statistical process control, and lots of terms that get written in textbooks which don't read easily, let's remind ourselves what we are trying to do when it comes to things like process capability analysis and statistical process control. And that is to deal with a process or manage a process or control a process. And a process is a set of interrelated work activities that transform inputs into outputs. Of course, that's a very textbooky, academic, theoretical definition, but essentially a process cannot be defined any more clearly than that. And it often relates to things like manufacturing, how we go through a process of turning raw material into an amazing product. And so statistical process control and process capability analysis are very common terms in manufacturing industries, because the manufacturing process is where these two tools relate the most. So before we look at what a process is, let's talk about what a capable process is. Now, a capable process is a process where the observed variation is largely within specification limits. So a specification limit defines what good is versus bad. Again, that's not a particularly useful definition. It's a very practical way of looking at what good outputs are versus bad outputs. But as a rule, there is no black and white, there is no binary good versus bad when it comes to manufacturing or any process. You usually have some nominal value that you want your ball bearing or your loaf of bread or your spring to adhere to, and the tolerances or the specification limits reflect what the design engineer typically thinks is an acceptable level of variation before your good product turns bad. But even when our product is close to specification limits, it is not necessarily as good as it can be. And we'll talk about what that means later on, because this is where we start talking about what a high quality production process is. High quality production process is a process that is in control and capable. Now, in control means that we use tools like statistical process control to essentially make sure that our process is doing what we expect it to do, what we want it to do. It's not varying out of control. It's not veering left or right for reasons we don't know about. So a process first needs to be in control. And once we have our process in control, we can focus on making it capable. So let's just do a little bit of revision for some and perhaps an introduction for others, and look at how we go about manufacturing sliced bread. Now, I know we don't usually use the term manufacturing when it comes to sliced bread. We usually talk about baking or bread production or food production, perhaps. But for all intents and purposes, the process that makes bread is analogous to any manufacturing process that is responsible for making something some sort of amazing component or product. And so sliced bread is one of the most useful foods employed around the world today. And of course, when we look at bread, we might assess its quality using terms like mass or crust color or the airiness of the bread or the number of slices or perhaps the thickness of the thinnest slice. We all have sliced bread scenarios where for whatever reason it was a little bit too thick or too long, and we just get the tiniest sliver of a slice at the end, which is not really useful. So essentially we need to throw it away. And so that might be something that's important for a consumer in terms of how they judge the quality of our bread. And sometimes we like making sandwiches where we don't want to have a huge variation between the size or the geometry of each slice of bread. And so minimizing the difference between the largest and the smallest slice is perhaps another way some people judge the quality of bread. But suffice to say, there are other things that play into what it is that makes a loaf of bread good or bad. It includes cost per loaf. So it's all well and good having a high quality bread, but how much does it cost to make that loaf of bread? Often there is a correlation between high quality and the cost of production, but that's not always the case. From a manufacturing perspective or a production perspective, we are interested in scrap, which is the amount of stuff we have to throw away because it's defective or we need to test it in a destructive way to make sure we're on track. We want to minimize scrap. We obviously want to maximize throughput, which might be measured in terms of loaves per hour. And these days, you're also interested in doing things like minimizing carbon footprints, minimizing environmental waste, etc., etc. So the process that makes bread is very important because bread doesn't generate value. The process that makes bread generates value. So if you're going to invest in a bakery, you're not investing in a set or a pallet or a group of loaves of bread. You're investing in the production process, the staff, the machines that combine to be able to create loaves of bread in an ongoing way. Okay, excuse me for 1 second. My phone has just called and it has just decided to wreak havoc with my headphones. I might have to cancel that. Fred, can you just let me know if you can hear me now?
Yep, welcome back.
Can I just get someone to confirm with a thumbs up that I can be heard? Thank you. Sorry about that. For some reason, my phone decided to call, hooked up to my headphones, and when I turned off the phone, my Spotify thing went nuts on my computer, which is why all hell broke loose. So I've just turned off my phone completely. So that's very unprofessional at my end. Moving forward, I need to remember to turn off my phone and not just have it on silent. So where were we? The process that makes bread generates value. It's not just the the loaves of bread that sit on a pallet. It is the bakery. It is the people. It is the machines that combine to make bread. So a process can be anything. It can be something that's that we can see, or it could be something that theoretically exists. For example, algebra and arithmetic are examples of processes which we like because when we have inputs, we always get the same outputs. 1 + 1 will always equal 2. But the processes we deal with are unfortunately random. Not every single loaf of bread will be the same. And so when it comes to a random process that is then formalized in a manufacturing process, we will have to deal with or have to control the fact that we will have a bunch of different outputs with different product characteristics, even when we do our level best to make sure every other variable or parameter stays the same. And so things like chewability and weight of our bread loaves will change over time. So not each loaf of bread will have a slightly different mass or chewability as we move on. Then there's process characteristics, the amount of money it costs to make bread, the production rate, temperature, uptime, all those sorts of things. These are process characteristics which obviously influence how we make our loaves of bread. Then there are byproducts like exhaust and scrap and waste. These are outputs, but they're not actually the products we're interested in. The byproducts, the things that we essentially have to get rid of, we can't avoid creating when we make a loaf of bread. Then there's different inputs we can control as well. So for example, the most basic input from one perspective is how we design our process. What does it look like? Do we manually create dough balls, or do we have a machine that does it for us? And then we have all sorts of other things that influence the random noise, which is also based on our process design, which will mean that even when we have a process that we're really happy with, there's going to be some variation between each loaf of bread. And these can be based on uncontrolled or uncontrollable factors, the climate, things like that, things that we just need to live with, or things that we've accepted we're going to live with. But then there are the controllable factors, such as the settings, the temperature settings, the technology we choose to use. The inputs can include raw materials, like the flour, the yeast, the water, the improvers that we need to make our wonderful loaves of bread. And then there are resources that go beyond these things, which include money, people, perhaps the most important resource. And with people, there is knowledge, along with the energy bill to boot. So that is a process, and that is an example of a process. So we need to be aware that processes are annoyingly, I should say, naturally vary from product to product. So how do we keep this potentially complex or complicated process in control? One way of doing that is with statistical process control. Now, statistical process control was a subject of the previous webinar. And the idea of statistical process control is if we are monitoring some characteristic, we want to look for statistical clues that our process is doing something unexpected. And that gives us as much early warning as possible from the point where we suspect something is happening, which is not what we would ideally like. And the time between that realization and our first product becoming defective gives us hopefully enough time to address whatever issue that might be causing that particular problem. And so with statistical process control, we often use things like a region or a zone where we expect 99 or more than 99% of variables to fall within should our process be in control. And so you can see here that our process is clearly starting to come out of control. Something happened, and the chewability of our bread is over time is not only going down on average, but the variation is increasing. And so we can use statistical process control, which comes with a bunch of different metrics and statistics, to help us identify as soon as possible when our process starts coming out of control. And a very common way of doing this is by introducing what we call upper and lower control limits, which contain more than 99% of the expected variables or metrics that randomly vary with respect to production. And this is just one way of helping us identify when our process starts coming out of control. There's a difference between out of control and outside of specifications. Usually our process will start coming out of control first before it creates defective products. And the key aim of statistical process control is to try and make sure we realize that point as early as possible. So what does that mean? Well, this means that we should be able to look at our process, monitor our process, really start understanding our process, work out what controllable factor influences what sort of characteristic of the output. And when that happens, then we start really knowing what it is we need to prioritize to take our process to the next level. And when we do that, we can identify what we call its capability, or the capability of the weakest part of your production line. So let's go back to the definition of a capable process. A process is capable if the observed variation is largely within specification limits. So let's look at what capability means in the real world. So if we instead of looking at our metric, chewability, for example, in terms of that vertical axis and horizontal axis representing time or production schedule, we can see here we have what we call the SL, LSL, and the USL, which stands for the lower specification limit and the upper specification limit. And we have in the middle a black line which represents the nominal or ideal value of the chewability of our bread. And up the top is my trademarked random hand of chewability. Now, this hand summarizes all the randomness, all the variation that exists in our bread making process that will lead which will lead to loaves of bread varying naturally in terms of their chewability. And when we make bread, it's quite an involved process. There's actually organisms involved which are required to raise the bread and introduce gas bubbles and all sorts of weird and wonderful things that make bread really, really delicious and yummy. But because there's so many processes involved, you would expect that there's going to be from time to time some natural variation around some ideal or central value. So let's just say we're going to produce lots of loaves of bread, and each one of these dots or balls here represents measured bread chewability values of a, for example, batch, or maybe the first loaf of bread per batch over an entire year, or the first loaf of bread produced every month, every day of the month, for example. However we sampled our loaves of bread, each one of these blue dots represents an individual chewability value. Now, it's really important to make sure we don't look at these loaves of bread as being all good. You should be able to see that the blue dots all line up within the upper specification limit and the lower specification limit. But the problem with that, and this goes beyond bread obviously, is that these loaves of bread, or these ball bearings, or these springs which exist towards the extreme values of what is considered acceptable, they're not as good as those loaves of bread right in the middle. So if we, for example, have lots of components which are manufactured towards the end or the extreme values of your specification range, these are the things that are going to introduce very, very subtle pre-stresses that then might create the perfect conditions for fatigue or early wear out. Or perhaps if we have enough of these components being manufactured towards the bottom end of the specification range, we can't easily manufacture them because we can't assemble them. They just, all these tolerances or deviations from the nominal value stack up, so to speak. And all of a sudden, when we have our 10 components that are supposed to fit neatly together, they just they don't fit as a combination because they are all some distance away from a nominal value. So when we deviate from our nominal or ideal value, we introduce conditions which make failure more likely and manufacturing more difficult. And then, of course, there are undesirable characteristics that our customers and our users don't want to experience. So when we have components which are manufactured towards the extreme ranges of the specification limits, that's when we get the rattles, the noises, the squeaks, the sharp edges, or our food doesn't taste as good, or our product can't be used in harsher environments, or it's just uncomfortable to hold. So we want to make sure that wherever possible, not only are we within specification limits, but we are trying to always get our product as close as possible towards the nominal value. This introduces many cultural challenges because a lot of managers, a lot of product line directors, all they want is to make sure that things are within spec. Because when things are within spec, they have done their job, so to speak, and they can stop spending money on improving their production lines. The problem with that ideology is that all they do is allow these conditions, these scenarios where we're in spec, but unreliable or unmanufacturable or undesirable to propagate later on. A number of catastrophes, well-known catastrophes across the world, were caused by the premature failure of complex machines that were manufactured in spec. Being in specification is not good enough. But we still need to have some idea about what it is to be good or bad. And so the upper specification limit and the lower specification limits are still very useful at helping us quantify how good our manufacturing process can be. So let's just say we want to improve our manufacturing process, or in this case, our bread production process. What we want to do is we want to have our chewability, in this case, as close as possible to our nominal value. So this means we are predominantly creating desirable products that have no manufacturing and reliability problems. Now, of course, you don't usually have reliability problems with the loaf of bread, but hopefully you can transplant this message into your scenario, your production line, into your production facility, and understand the key message. If we can get our components and our products as close as possible to our nominal value, we will all of a sudden start creating desirable, reliable products, and that's what we are trying to do primarily. So you can see here that this scenario where our chewability is now a lot closer to this nominal value, this is clearly a better manufacturing process or a better bread making production process. So we can see that it's better, but how do we measure how much better it is? How do we measure capability? Because capability is what we were just looking at, the ability for most of our variation or deviation to be within our specification range. So how do we measure it? Well, to measure it, we do need to use a little bit of statistics. Now, this is what we call a bell curve. Many of you might have heard of the bell curve. In my courses on statistical process control, we go through where this bell curve comes from, because we see this bell curve in so many natural phenomena. And the reason we see it is because it's based on this thing called the normal distribution. And the normal distribution just so happens to model processes where lots of things add up in a cumulative way. And that could be, for example, the amount of time our bread spends being baked, plus the amount of yeast that was put into our raw ingredients for our bread, plus the amount of time our bread was allowed to rise beforehand, plus the temperature at which that bread was allowed to rise, etc., etc. Now, if there's minimal variation in those inputs, as a rule, they tend to add up, which means the variation we see tends to follow or tends to fall in this beautiful bell curve shape. So this bell curve represents the likelihood that certain random variable values will be within certain ranges, for example. And so if you need to understand more about the bell curve, I really encourage you to go out there and learn about where the bell curve comes from, including this thing called the central limit theorem. Now, we're not going to go through that today, but suffice to say, we do see the bell curve in a lot of manufacturing processes because the characteristic bell curve is modeling tends to be based on the addition of lots of different inputs and controllable factors. Now, the mean of our bell curve is right in the middle. And we represent the mean of our bell curve with the Greek lowercase letter mu, which you can see on the screen right now. So the bell curve just happens to be symmetrical. It happens to be the left-hand side looks like a mirror image of the right-hand side, which means the mean is right in the middle. The mean is not always in the middle of distributions like this, but for the bell curve and other distributions which are symmetrical, it just so happens to be right in the line of reflection. So this line here represents the mean. Now, if this was measuring for example, the chewability of our bread, this would tell us or help us understand the extent to which the chewability of our bread varies about the mean. Now, the normal distribution or the bell curve uses this concept called the standard deviation. The standard deviation is exactly that. It is a standard that human beings have come up with to try and quantify the extent to which random values vary, I should say. And that means that I can say if one process has a mean value of 10, but a standard deviation of 1, I know that there's going to be more variation involved in it with another process with a mean of 10, but a standard deviation of 5, for example. It just gives us an idea about the extent to which random variables vary about some central value. Now, if we are using the bell curve, or if the bell curve, I should say, turns out to be a really good model for your process, your product characteristic, then we know that about 68.27% of normal random variables are within one standard deviation of the mean. So that's a little bit over 2/3 of all random variable values will be within one standard deviation of the mean. Now, for those budding statisticians out there, this only applies to the bell curve or the normal distribution. Every other probability distribution out there has a standard deviation, but none of them will have this exact property. This is unique to the bell curve, where we see 68.27% of random variable values within one standard deviation of the mean. Okay. So we often use the Greek lowercase letter sigma to represent standard deviation. So what we've done here now is we've looked at our bell curve and we're looking at a region which is within 2 standard deviations of the mean. So you can see that this shaded area goes from -2 sigma to +2 sigma, where sigma represents a single standard deviation. So we've gone twice as far out again, and this region now includes 95.45% of all normal random variable values. And if we keep going out, so to say to three sigmas or 3 standard deviations above and below the mean, this region, this interval will contain 99.73% of all normally distributed random variables. And this is a characteristic we see over and over and over again. And we often use this sort of standardized 6 sigma interval to help us characterize the extent to which most random variable values will vary. 99.73% is not 100%, so there's still a chance that a random variable value will go outside this range. But just for the purpose of trying to capture or imagine or understand or visualize how much these variables are going to value away from the mean, we tend to settle on a combined interval of 6 sigma or 6 standard deviations to sort of summarize the likely range of our random variable value. So it's important to understand this underlying concept that we often use the bell curve in manufacturing processes. It is often a good model to use because manufacturing processes tend to add up in a way, but you need to really double check that your manufacturing process or whatever process you're responsible for is well modeled by the bell curve. The bell curve is a really good model most of the time, but you need to double check because there are some scenarios where you need to use an alternate model. But most process capability analysis and statistical process control comes back to this normal distribution. So let's just say that this bell curve here with its 6 sigma range represents the chewability of our bread based on the production process of our bakery. Now, before you started creating our bread, we obviously defined or came up with upper and lower specification limits for the bread chewability. And that's fantastic because that gives us an idea of what good bread is versus bad bread. And you can see here that most of our bread chewability values are within our upper and lower specification limits. So visually, this looks like our process is, let's just say it's good. The bell curve seems to be nicely contained within this range. And so that is a good visualization, perhaps. This represents a process which seems to be largely capable because most of the variation is within specifications. So one way of quantifying the capability of this process is by simply dividing the specification range, which is a difference between our upper and lower specification limits, by this value 6 sigma. Remember, 6 sigma represents the range within which we expect 99.73% of random variable values to fall within. Now, this value here, C subscript P or CP, is called a process capability index, which in this case is 1.18. So because this starts to quantify how capable our process is. The higher the value, the more likely it is for our random variables to fall within our upper and lower specification limits. But there is a problem with this capability index. And the problem with this capability index is it doesn't really take into consideration where our random variables are going to be centered around, where our typical chewability values are. So for example, if our process starts creating chewable bread where the chewability increases, but the variation doesn't change too much, this particular capability index will still give us the same value because the variation hasn't changed, even though it's starting to move outside our specification range. And you can see here that we are now creating a lot of defective loaves of bread. In this case, you'd be expecting maybe 15 to 20% of our loaves of bread to be outside of specification, which is undeniably too much. So this capability index is good at sort of quantifying the variation, but not good at quantifying the extent to which that variation means our process is creating products outside of specification limits. So we do see this capability index a lot, primarily in textbooks, but as a rule, we need to use something better. So let's look at our original process, creating bread with chewability values like this. And now we're going to take into consideration where this bell curve sits. It's all well and good to work out to quantify how fat or wide our bell curve is, but we now need to take that into consideration in addition to where that bell curve sits on our chewability axis, I should say. So let's now go back to the mean values of our bread chewability. And we're going to, instead of looking at 6 sigma, look at 3 sigma, because we're going to focus on what we call a directional approach to capability indices. And so if I find the mean of our loaves of bread, or sorry, if we find the mean of the chewability of our loaves of bread, then we can come up with these ranges here. We have 3 sigma and our upper and lower specification limits minus the mean. So we have our ranges which extend 3 sigma above and below the mean, and ranges which extend from the mean to our upper and lower specification limits. And the idea is that we can now create this expression here. We can now divide the lower range by 3 sigma and the upper range by 3 sigma to come up with this different capability index, CPK. And the idea is that CPK finds the minimum value which represents the mean to specification limit range divided by 3 sigma. And all this does is make sure we capture how our bell curve sits, or the location of our bell curve within the specification range. Now we have on the right-hand side a value of 1.11, which is simply the upper specification limit minus mean divided by 3 sigma. That's how we find that value of 1.11. And because that is smaller than the corresponding value on the left-hand side, that is a value we use. The idea is that if our bell curve, if our process starts to move up and starts to create these loaves of bread, which are now outside of specification limit, then our CPK capability index will pick that up. So all of a sudden you can see that our new value for CPK, which is based on the right-hand side, is 0.37, because this gives us a minimum value where we divide the specification limit divide the distance between the nearest specification limit and the mean by 3 sigma. And so for this reason, we often use CPK a lot when it comes to manufacturing and process control, because CPK considers the mean value. And what does that mean? It means that we will take into consideration both the variation in our process and the location of our product characteristic if it slowly moves outside of specifications. Some of you might be saying, well, that's all well and good if I have an upper and lower specification limit, but what happens if I only have one? And this happens a lot. We often have a specification limit where we need the product characteristic to be either greater than or less than that value for it to be considered okay. Well, all we need to do for our CPK is essentially focus on the specification limit that matters. So for example, if we only have a lower specification limit, then our CPK expression looks like this. And you can see here that if this is our process and we have a lower specification limit that far away from our mean, CPK is equal to 1.97. As a rule, when you're approaching the values of 2 for CPK, that's considered world class. 2 is very, very good. On the right-hand side, though, if we have an upper specification limit, which is this close to the mean of our process, we have the natural variation routinely pushing our loaves of bread beyond the upper specification limit, then our CPK value is simply 0.37. And that reflects the fact that we are creating a lot of defective bread over here. So that's bad. So we want CPK values to be as high as possible. That represents good, high quality components and products. But what does CPK actually mean? When you talk to people who have been in the business and they say, well, what is CPK? Well, it's a capability index, and the higher the value, the better. But what does it actually mean in terms of defects and the amount of products you manufacture, which are outside of specifications? Well, CPK is actually one way of essentially quantifying the probability of you creating defective loaves of bread. So if we go back to our random hand of chewability, and we look at this particular scenario here, where you can see that we have a bell curve which characterizes the chewability of our bread. And you can see that most of the values, if not all the values we have sampled, lie within our upper and lower specification limits. So I'm going to ask a show of hands. Who thinks this is a good or capable process? I'm going to ask people who think this is a capable process to raise their hand, and we'll see. And I'll ask you also. So the next question I'll ask after this is, I'll start that request again. Those of you who think this is a capable process, please raise your hand now. I can see one. And those of you who don't, I'll ask you to raise your hand very shortly. So we have three or so people who believe this is a capable process. Okay, fantastic. So before I move on, I should say, who believes that this is not a capable process? Show me your hand if you think this is not good. So I can see 2 hands up in the air. Okay. And the reality is there is no such thing as good or bad. It is up to you and your organization to work out what good looks like, to the extent that you should understand what is the likelihood or probability of you creating defective products. So this particular process here has a CPK value of 1. This is what a process with a CPK value of 1 looks like when it's perfectly centered within our upper and lower specification limits. Now, this means that we would expect a few products to be outside of our specification limits. But if we decrease our capability index to 0.67, we can see that our bell curve becomes shorter and fatter. And now you can see that we are starting to create defective products outside our upper and lower specification limits. Now, if your process has a CPK value of 0.67, that means on average, you are creating 45,500 parts per million defective products. So 45,500 out of every million products are defective if you have a CPK value of 0.67. If we go back to our CPK value of 1, you would expect 2,700 parts per million products to be defective. Now, as a rule, that is actually considered way too high. 2,700 parts per million is often unacceptably high when it comes to manufacturing, production, scrap, and yield. So even though it looks like most of our products in this sample are within our specification limits, and in fact they are, you would expect that 2,700 out of every 1 million products you manufacture to be defective. If we keep increasing our capability index, say to 1.5, then we can reduce our defect rate, I should say, to 6.8 parts per million. So you can see here that even for moderate increases or improvements in CPK, we really reduce the number of expected defective products for our production process. Now, if we increase our CPK again to 2.00, which is often considered to be very, very good, we reduce our defect rate to 0.002 parts per million. And so we can actually create this chart here, which relates CPK values to the defect rates. And the idea is that we want to improve our CPK or increase our CPK values such that so that we limit the amount of defects we are creating during our production process. And not only do we need to focus on meeting quality goals, but if our bread, for example, has 3 what we call critical to quality characteristics, such as chewability, such as mass, what's another one? Just to say perhaps height, the height of each loaf of bread, then for us to make sure we meet our quality goals, we need to make sure that our defects based on all 3 characteristics don't add up in a way to create enough defective products to exceed the allowable number of defective products our quality goals suggest we need to have. So this is what process capability analysis is all about. We pick a capability index like CPK. We need to have that capability index aligned with some quality goals. It shouldn't be just picked from the blue, because that then allows us to meet our quality targets. Now, some textbooks out there will suggest that there are acceptable levels of CPK. So, for example, if your CPK is 1, some textbooks will tell you that that is okay if you have a robust screening process. That means that your production process has a CPK value of 1, 2,700 products out of every million products you manufacture are going to be defective, but you then have some sort of screening process to get those defective products off your production line and otherwise prevented from getting into the hands of your user and customer. Now, that is really not ideal. You don't want to have quality baked into your product through a screening process. That simply wastes money. And it also means that you're going to have more and more products which are deemed acceptable, but are still very, very close to your specification limits. And as we know, that's not a good thing. So other textbooks will suggest that you should be aiming for a CPK value of 1.67 if this is a brand new process. We're using new technology, but you can also aim for a CPK of 1.33 if your process is not new, it's embedded, you've been using it for a while. Some people will say, some texts will say you need to aim for a CPK value of 1.5 if your process is brand new and you only have one specification limit, i.e. not both. But if your process has been up and running for a while, then it's okay to aim for 1.25. Other organizations suggest you need to aim for a CPK value of 2. And essentially, that's what Six Sigma, the Six Sigma thought process is all about, that you should be aiming for a CPK value of 2.0 for all your product characteristics. Now, this is not great guidance in a way, because it allows you to think that all you need to do is get your CPK value up to a certain number. But how does a textbook know if 177 parts per million defects is okay for your organization versus 1.59 or 0.57 or 63.3 or 13.6 or 6.8? You should be coming up with your own quality goals and work out how many defective components or products you can tolerate, so to speak, and then work out what your CPK value should be thereafter. But not only should you work out what your quality goals are first, you need to allocate CPK to every single characteristic that is going to contribute towards your product being defective or not. So if you have lots of critical to quality process characteristics or product characteristics, I should say, then the CPK value for each one of those needs to be considerably higher, because they will all add up and all combine in a way to essentially drive your overall process CPK down. So when it comes to process capability analysis, understand that things like CPK are really, really good at characterizing the variation that your process will impart on outputs that matter. And that can be loaves of bread, ball bearings, springs, anything else that you're responsible for manufacturing. CPK represents the extent to which your product characteristic is going to vary with respect to your specifications. So it's a very, very powerful tool. You will also read, like I said, textbooks which say this is what you should be aiming for: 1.25, 1.33, 1.45, 1.5, 1.6, 1.67, 2.00. And you might get confused about which one you should be aiming for, and that's because they're just arbitrary values. You need to work out what your quality goals are first and then come up with your CPK values. And the reason why we want to use CPK is because your technicians and your manufacturing engineers who are going to be conducting things like statistical process control find CPK really easy to calculate. Now, we go through how we do that in other lessons, in other webinars, and other courses, but this CPK value is now essentially a metric that many well-trained manufacturing technicians can understand. And so if you say, hey, we need to have a CPK value of 1.38 for bread chewability and 1.49 for bread mass, you are starting to convert your quality goals into a language and metric that matters to your manufacturing technicians. So you should never just go out and arbitrarily choose a CPK value based on what a standard or a textbook says you need to do. You should work out what works for your organization and allocate your goals accordingly. And the reason we use CPK is because it allows us to convert defect rates into these CPK goals, which are very useful for our manufacturing technicians. And so I'm going to leave the discussion on process capability analysis right there. I'm going to leave this slide up on the screen, and I'm going to ask if there are any questions about what we have covered today. I'll just ask that the two gentlemen who have raised their hands, please drop their hands from the survey, so that if anyone wants to raise their hand or otherwise ask a question, please feel free to do that right now. Any questions about what we've covered in today's webinar as it relates to process capability analysis? And while everyone is ruminating, I need to emphasize that before you can think about process capability analysis, trying to measure the variation of your process with respect to specification limits, your process must be in control. That means it's not deviating all over the place. It's not going up and down without you knowing why. The variation is not changing from batch to batch. You need to make sure that your process is in control, so that the next day you turn your process on, it will produce the same variation from your batch of products. And the reason you want to do that is because if you don't confirm your process is in control before you come up with a CPK value, then the next day it's going to be a different CPK value, and the day after that it's going to be a different one again. So make sure your process is in control. So Kevin asked a really good question. I hear a lot about 1.5 sigma shift. Can I explain? And yes, I can. The idea is that a lot of schools of thought, including Six Sigma, suggest that your process capability will drift by 1.5 sigma over time. So that means that if you start with a process that has a value of 2, a CPK value of 2, if your process drifts and your bell curve becomes a little bit shorter and a little bit fatter, your process capability index of 2 should theoretically drop to 1.5 over time as your machines age. So let's see if I can find, I'm going to go back to some of the slides we looked at to try and illustrate this better. So this is what a process looks like with a CPK value of 2. And so the 1.5 sigma shift means that if we start off with a sigma CPK value of 2, as your machines age, you would expect that your variation will start to look more like this. Oh, it's not going to stay there for me. Let me go back. Start to look like this. All that means is that these schools of thought are trying to estimate that there will be some unavoidable degradation over time of your machines and your processes and your humans that are in charge of those machines, et cetera, et cetera. So you should aim for a CPK goal that exceeds your ultimate CPK requirement by 0.5. And the reason why I use 0.5 is a sigma shift of 1.5 sigma is means that your CPK value will decrease by 0.5 if you go through the math. So that's where this 1.5 sigma shift comes from. The idea is that you aim at the start of your production process for a capability index which exceeds your goal, because over time your process will degrade and essentially introduce more variation into your outputs. So if you incorporate this 1.5 sigma shift, it allows you some production margin over time. But in practice, you should really be monitoring your CPK values as your process is used and your machines get old. Does that answer your question, Kevin? Awesome. Jacob asked the question. This is based on a mean value being the optimal set point. What if our goal is to maximize and get closer to a USL or an SLL? This is theoretical, of course, but I know there are some statistical models where the goal is to still obtain a maximum or minimum of some feature. I think I know what you're talking about, but I'm going to challenge your definitions, because as a rule, well, as a USL is defined, or LSL is defined, that is the boundary between good or bad. And there should be no no process where we're trying to aim to get as close to that boundary as possible. What I think you're talking about is what we call a nominal value. So on this screen here, you can see that we have a nominal value here, which is based on, which is in this case, the midpoint. And so in this case, our design engineer said, hey, the upper specification limit is 10, the lower specification limit is 8, but our ideal value or our nominal value is 9. So we want to optimize and get closer to a nominal value. I think your question is that in some cases, the nominal value is not in the middle of our specification range. Is that correct, Jacob? Right. So, well, so Jacob said that pretty much in instances of skewed bell curves. Now, when we have skewed bell curves, just to be clear, a skewed bell curve models or represents the variation in your process. So a nominal value, which is closer to one end of the specification limit versus the other, doesn't necessarily mean that your product automatically has a skewed bell curve, so to speak. So let me just try and go back to this screen here, where perhaps I can do some drawing. So I think Jacob's talking about a scenario where instead of our nominal value being this one here, it is over here somewhere. And that happens from time to time. Our process could still have a bell curve, like our process model could still be a bell curve like that, but we might have a nominal value where it's not in the midpoint of our specification range. Sometimes our processes do look like that, have a skewed bell curve, et cetera, et cetera. And that is where CPK falls down, because it essentially assumes that, that the optimal value is in the midpoint of the range. One approach is to use the Taguchi loss function, which allows you to essentially skew your measurements. Another approach is to simply, instead of having a uniform scale each side, we normalize it a bit, so we have a scale where this side over here is stretched out that way. And that way you can sometimes use CPK based on this normalized scale, where essentially we apply transformation to our random variable values to at least visually have our nominal point look like it's in the middle, even though it's not. I'm more than happy to talk about that perhaps outside of this webinar, but you do raise a very good point where sometimes we need to have nominal values which are closer to one specification limit than the other. And you need to, in many cases, tailor your capability index to your organization based on that. So if you do have any of those questions moving forward, Jacob or anybody else, I believe due to time, we'll have to take it outside this webinar, and I'm happy to answer any emails you throw my way. Derek, can you, thanks Jacob, can you speak to non-parametric and parametric data and the importance of finding the correct distribution? Okay, yeah, the importance of, so finding the right distribution is very, very important. And when I teach statistical process control and process capability analysis, I actually have a spreadsheet application which does all this for us. It allows you to do some rudimentary model selection, because every single statistical process control guidebook and standard and textbook assumes carte blanche that the process you're modeling is modeled by a bell curve. And that is a dangerous assumption to make. In fact, they go a couple of steps further than that, because when these control charts first came out in the 1920s, statisticians had to essentially provide constants to the manufacturing engineers that allowed them to make rudimentary guesses about what the sigmas were and the standard deviations were based on their observed sample ranges. And for whatever reason, software packages to this day incorporate those constants as opposed to estimating standard deviations and things like that directly. So most of the approaches that you will see in software is essentially non-parametric in that they simply find, you simply put the data in and it finds mean and standard deviations, but then automatically assumes it's parametric by everything after that is based on the underlying premise that this is a bell curve. So it is hugely important, and the answer to that, a full discussion on this topic is outside the scope of this webinar. I'm more than happy to, again, extend this conversation via emails afterwards, but you cannot rush into statistical process control or process capability analysis without confirming that the underlying model has a bell curve. A lot of the time we see a log normal distribution because which is that skewed bell curve that Jacob was talking about. That occurs very naturally in many random processes, and that's okay. But you can't use CPK based on that random variable. You have to do what we call a transformation, I should say. And once you do that, then you can start using CPK. But most software packages and most production guys and consultants out there will just simply assume that the bell curve, the normal distribution, holds sway, and you can get some disastrous results or metrics when you don't understand the underlying model. And again, I can speak to you, Derek, via email after this about how we can do that, but you need to make sure that your process is modeled by a bell curve before you use statistical process control or process capability analysis. Does that come anywhere close to answering your question or request? Haha, Kevin, concur. This highlights the importance of knowing the theory as opposed to plug and chug. I haven't heard of plug and chug. I know exactly what you're referring to, and I'm going to shamelessly borrow that and steal that in future conversations, Kevin. That's fantastic. Just putting any software package or Excel spreadsheet will give you numbers. Whether you know what those numbers mean or not is a different question. Any more questions? Absolutely. So Derek's mentioned that he uses a distribution finder and Minitab. Big help to find the correct capability, CPK or PPK. Just understand that Minitab, for whatever reason, is one of those software packages which still uses those estimates that were derived for our manufacturing engineers back in the 1920s. And as opposed to actually calculating, for example, the sample standard deviation, it still uses those constants to find out those standard deviation estimates. I don't know why. It introduces inherent inaccuracies, but what you do in terms of using a distribution finder and Minitab to confirm that the bell curve is modeling your process is a very, very mature and useful step to incorporate in process capability analysis. And I haven't even spoken about PPK yet, because that's a whole webinar in its own right. Long story short, a CPK measures your process, your machines, your humans. Or PPK measures your products. That might sound weird and different, but essentially CPK measures what would happen if I turn the process on right now. PPK describes what happened for your process over the last year, for example, with all its errors and issues and faults and instances where it came out of control, and you then fix it and put it back in control. How did your loaves of bread behave overall as your process went routinely into and out of control? So CPK reflects your process, which would hypothetically, how it would hypothetically influence products if you turn it on right now. PPK is based on the products you actually created or manufactured. Any more questions? Okay, so if there's no further questions, I'm going to leave it on this slide where CPK, the capability index, which measures the variation associated with your process, is essentially another way of characterizing how many defects you're going to, or how many defective products you should expect per unit batch or per unit run or per unit time. And so if you know the CPK, you should know your defect rate, and you can convert it to parts per million, for example. A lot of textbooks will tell you that this value of CPK is optimal or the minimum acceptable value. And I suppose if you've got nothing else, that's great advice. But realistically, if you have your own quality goals, you should then allocate CPKs to your individual process characteristics. If you do want to incorporate that 1.5 sigma shift, which is not a problem, by the way, especially if you're going to start, if you're at the start of your production run, then simply allocate those goals to your quality characteristics, and then add 0.5 to your CPK goals. But in practice, you shouldn't just set and forget. You should routinely, in addition to things like statistical process control, conduct process capability analysis, see if your CPK has changed, and if so, work out if you need to do something about it. Any more for any more? Thank you, Kevin. And of course, with that, you got the guidebook with you, which contains everything we talked about today, plus a little bit more. Thank you, Sebastian. If you do have any questions, you have my contact details. My contact details in the front of that workbook. And then we will see you, not necessarily see you, because the next webinar I'm doing is on reliability growth. And manufacturing engineers often don't touch reliability growth. And I'll see a whole new swathe of attendees for the next webinar. But if you do want to join me next month, that's what I'll be talking about. So thank you for your feedback, Jacob and Patricia. And don't forget to reach out if you have any of those questions. Beyond that, hopefully this will help you optimize and improve your processes and help you create high quality products without having to spend a lot of money working out which thing you need to optimize or what your goal should be.